So welcome to the second in our series of design and manufacturing seminars this semester. It is my great pleasure to welcome a great friend from many years, Professor Saitou, from some university up in the North Country. So a little bit about our speaker today. He received his bachelor's degree from the University of Tokyo, master's and PhD from MIT, all of them in mechanical engineering. His research is in computational design generally, manufacturing, assembly. He's received many awards, including the ASME Toshiba Award for Design for Manufacturing. He's had a couple of stints as associate editor of the ASME Journal of Computing and Information Science, JSci. So thank you very much for that.
I'm still doing. I'm
very,
again.
Very special to me. And also Journal of Mechanical Design, both ASME transactions. And he's been very active with our ASME community. He's done a lot of service. Serves as chair of ASME Design Automation Committee, chair of the ASME Design Manufacturing Committee. And he's a fellow of both ASME and IEEE. So please join me in welcoming Professor Saitou. The title, of course, is up there already. So, yeah, maybe we can leave that open.
Okay. I did. Thanks for coming. I did a little bit of unusual practice for me to put some slide before the title, because I understand this is for a general audience, although those are mechanical engineering students. So this talk is about topology optimization. So I thought I would put a few slides about topology optimization, what that is, and what I am contributing in this area. So this is really the one picture slide about topology optimization. This is a computational design method for structural products or structures that allows the geometry to be almost like anything, so that it doesn't actually assume any parameterization in the shape. So that it's a very much really a top-down method for designing structural shapes based on the boundary and loading condition. And the only thing you have to specify other than boundary and loading condition is to where things should exist after the computation is done. So very the little limitations. And what it does is that then it does a lot of computing, which I will probably touch on a little bit. Then you come up with this one. And so it is really essentially the problem of material distribution, where to find the location material should exist within, of course, the fixed boundary. And, but because of that, if you impose any additional, say, constraint, which I will impose, but you could make any shape. Okay, so that is actually a big advantage of this method. Now, of course, I'm not the inventor of this method. We actually building on top of this development, trying to make it better. So that's really the background. So it's been a little bit, about 30 years since the method has been invented. I guess most humbly it was invented, in part the big contribution of the researcher at the University of Michigan, but not me, of course. So it was initially looking like this. It's like, okay, although the principle is there, it's like, most like some kind of the cloud image. Okay, that was what could be done, what they could do best, 30 years ago when it's invented. Now after 30 years, now there are commercial products, number of them, can do very sophisticated computation on the numerical tricks, so that they could do things like that. It's very impressive. So we came a long way. And there are a number of commercial products you can buy. And also, if you probably know, that the advent of additive manufacturing sparked this kind of interest in this area again, because there seemed to be a good marriage between the geometric versatility of additive manufacturing versus geometric versatility of designing such structures using this method. So that was kind of a big background. So the gap I want to fill, hopefully during this lecture, during talk, is that between this. So this is like really the state of the art of topology optimization using commercial software. But then this is what you see, exactly things like that in the real world. So the things are not one piece, basically. This is, indeed look like one piece, but it indeed is computed and modeled as a one piece. And that was really the big limitation in topology optimization. In that, it can do small things, which it's really a one piece, then the result is one piece. It can do very clever geometry and a fancy design. And nowadays, you can directly produce, mostly from additive manufacturing. That's good. But things that big, nobody makes the car body like this. It will be looking like this, many parts. And that was the gap I'm trying to. First, I tried to ask myself that why is the case, and then I found one reason for that, and then tried to fill the gap computationally by identifying the reason. So basically, there's a gap until now, and that's the talk. So now let's come back. Okay, and so the title says. Manufacturing-driven. So that is really the key word, and which is, I think, is one of the main reasons why there exist such many parts in the structural products. And if you implement that, if you incorporate that aspect into this computational framework of topology optimization, you could actually synthesize as a outcome of optimization multi-component systems as a output. And that is really the extension I'm adding to the conventional topology optimization. And that enables a top-down design of structural assemblies instead of structural products, which is monolithic. Okay. So that's the. And of course, I have to acknowledge that first of all, these are not really my work for me in large regards. Those are the work done by a number of PhD students, visitors, collaborators, and these are a subset of people who did some work on the result I'm showing today. And not to mention, of course, sponsors are always important, and at the beginning rather than the end, because oftentimes I run out of time and I cannot complete the sponsors. Okay, so outline today, I wanted to spend some time on convincing you, hopefully, that why there are so many parts in many of the structural products you see out there. And my point, my claim is that that's due to, in part, at least, due to the manufacturability of the chosen manufacturing process to use to produce the product. And then this is a little bit of academic history of what this has been done in this area as an attempt to incorporate multi-component aspects to the topology optimization. And then the formulation we introduced to enable the multi-component within the framework of computational framework of topology optimization. And MTO-X is the kind of acronyms we've been using to try to highlight MTO framework applied to this process, that process, and so on. So far, we have done MTO-S, sheet metal stamping, MTO-D, die casting, MTO-A, additive manufacturing, MTO-C, composite manufacturing, and so on and so on. And I'm going to go through quickly what can be done using those basic framework as well as the X formulation, which is really the process-specific manufacturing constraints I'm adding to the generic form of optimization problem. Why so many parts? So this is how the car body is initially made out of the CAD, or maybe even before the CAD. It was one piece. It's a clay model, doesn't have any parts, welding, and anything. Because the shape is, has its own function, aerodynamic and stylistic. Okay, but that itself does not necessitate the body being lots of pieces. Okay, and but then the outcome you see is really like that. So there must something in between happening, so that some people decided that okay, it's better for some reason to make it in so many pieces. And so I've been pondering this problem for many years and trying to find the reason why people do that. Because to me that there must be a good reason to go from here to go here, because it looks like there's a lot of effort to first to produce so many parts, not to mention joining later to make it like this. So there must be a good reason to do that. Along the line, I was actually having some thought when we putting together my notes on class of design for manufacturing. So this is a famous picture from Boothroyd's book about the benefit, trying to illustrate the benefit of applying DFA, or design for assembly principle they proposed. So all right, this is before DFA and this is after DFA. So the benefit is that, part counts reduced, there are fewer parts, and with potentially the price of more complex geometry, somewhere around there is all like integrated together, so that it's got the one piece. Okay? And because of that, you got the cost reduction and everything good. Okay? So usually this picture is supposed to read from left to right, okay? Meaning that before and after. So before was bad, and then after is good. Okay? And so that's how the book is written. But one day I realized that, what if I look from opposite, right to left, from here to here? Okay? And then I thought of one thing. Okay, if I look from here and then move to this one, maybe something must be happening. So this was obviously made by injection molding. Geometry tells you that this is the injection molding. And but then what if I cannot use injection molding? What if I have to really make it so that maybe the deep drawing and sheet metal bending is only the process available to me? Obviously I cannot make this geometry. I have to do something. Maybe do that. This indeed was really the natural design. At least in these parts, natural geometry suitable for sheet metal bending. Okay. Maybe this was injection molding in the beginning, but this was obviously assuming a different process. As a result, this can get more pieces decomposed or partitioned because of the choice of manufacturing process you made. And when I realized that, maybe that was the reason the clay model one piece will be become so many pieces of parts in the real factory setting. So when I view this assembly design, I am viewing this is more like, okay, I have this one piece blob of a clay model partitioned into multiple pieces. But then I was seeking the reason for partition, why you have to do that, why it's good for you to do that. And my conclusion, based on this, the right to left observation of the DFA figure, is that I divide because it would be too expensive otherwise, based on the chosen manufacturing processes or available manufacturing processes. So, yes, I will start with this clay model, one big piece, but then in between the partitioning to 1,000 pieces of components, there's a decision regarding that, okay, I would use sheet metal forming and spot welding to make it. Then, all of a sudden, all right, because it's a sheet and it can deform this much and has to have a certain geometry and topology limitations, obviously I cannot do that. Because of size, maybe cannot be too big, and the curvature cannot be too large, and so on, so on, so on. End up being like this. So that was the reason, at least that made sense to me, to rationalize this seemingly unnecessary process of taking this one-piece design to multiple pieces when you bring the design into production. So that was, pretty, now it's convincing, okay? And we've been doing a little bit of effort before, we can reach this point of solving computationally modeling and realizing this process in computational design framework. But I soon realized that maybe I could do that, meaning that instead of starting with this fixed clay model, which is actually designed by its own certain criteria, like aerodynamic, stylistic, other things, okay? And then, okay, I'm done, and I'm give that to you so that you decompose because you are a sheet metal manufacturing engineer, okay? Rather than doing that, maybe I can do that. Meaning that, okay, I take some requirement, just like the initial big blank you had for the topology optimization, which only specifies a requirement. Design must stay within this box, and then a bounding and loading condition is the requirement for the product. Okay? And then, maybe I will actually do design of the shape as well as the partition into manufactured pieces simultaneously. Okay? And so that's really what I view this MTO method we have developed will do. So really, instead of I divide because it will be too expensive, now I design and divide because it will be too expensive to output. So it's more like I start with something, I don't know what I'm designing, but I know the requirements. But I sort of know that this must be the process I have to really rely on. Then can I come up with this? Simultaneous design and partitioning. I kind of call it SDAP. Okay, that might be the things we wanted to attack. And so a little bit of history. Of course, we start out with this initial figure of starting with a circle, end up being a partition of the circle itself. So the fixed geometry. So this one was where we started. But I started with the outcome of a TO result, topology optimization result. So this was fixed TO result, so that I just don't do any topology optimization. I just got the result. Okay. But the result is the one piece. Okay. And then can I apply the geometry constraint specific to the chosen manufacturing process so that it will be partitioned to the pieces, each of which can conform those constraints. And that was the earlier effort we did, really the beginning, in the earlier days of my career, to partition given geometry. And at this point, we are assuming stamping and subwelding is, of course, considered process, although the result doesn't look anything like the stamped product because of the lack of details. But the principle is there. So I applied the constraint imposed by chosen manufacturing processes to motivate the decomposition of a given fixed input geometry initially. So I did that for the a little bit more complex geometry, but the principle is the same. It's a fixed geometry FE model of a one piece, say mid area of the body, and I just did the decomposition. Partition is the only thing we did. Again, applying this stamping and spot welding as a driver for partition. Okay. Of course, while you're doing it, you have to look out for original specification of the product, which the one piece was designed for, which is typically some kind of structural performances, which original one piece design was designed for. You have to keep on watching the impact while you're applying for the partitioning. And typically, you partition it, your performance goes down because one piece is typically the best. Okay. But then your idea is that you will cut into pieces in such a way that the negative impact to the overall performance is minimized while you are satisfying the manufacturability of each cut component. So that's really the process this optimization is trying to achieve. So then, later on, then maybe this is something we could do. So we start slowly moving into this simultaneous design and divide. So initial work is a little bit of design, not much design. Okay? So we start with this skeleton and try to decompose by applying joints with a specified area. And so at least we start to do a little bit of design by changing cross-section of the beams. Because everything looks like a beam, because it was assuming different manufacturing process here. It was supposed to be a fancy space frame body with those tubes are made by extrusion. And so dissimilar to stamping we have been considering, this one is extrusion, so the chosen manufacturing process is different. And if you choose different manufacturing processes, it will impose different manufacturing constraint. In this particular case, extrusion obviously cannot produce branching beams, right? It has to be all straight beams. Bent, yes, you can bend it, but you cannot do branching. Okay? So the branching is eliminated, you see, and by the partitioning, and the penalty on the certain angles of bending. So that if you have a 3D bending, it'll be more expensive than 2D bending, and the bending angle has some impact on the manufacturability. So you try to cut into pieces in a somewhat reasonable manner. Okay. But this was trying to illustrate that the principle applies for the different type of manufacturing process, as long as appropriate geometric constraints imposed by the chosen processes identified and appropriately applied. Okay. And slight design. Okay. Not much design. Now, okay, so can I do a little bit more design side of it, so that we could do what they call like a ground structure-based topology optimization, which is rather than doing something like made of small pixels, you start with this kind of network of beams. Okay, and the idea is to basically, erase something you don't need. Okay, and but then your choice is limited by this network initially.
And how do you get the initial?
How do you get the initial is just like how do you get the initial mesh, and then yes, it's really
That's going to affect.
Yes, and this is inherently dependent on the initial choice of what they call the ground structure. It's a ground structure approach. So how to define ground will affect the outcome. Yes. But the advantage of that is that it's very easy, quick, and intuitive to implement. And that was the first thing we did. Yes. And I'll talk a little bit about this the input dependency in the continuum optimization of topology optimization. To do with this mesh dependency problem, which is it can be solved by the way the purely mathematical formulation, which we do for the latest the 3D implementation. But this one surely has elementary and primitive. Yes, how you make this one is really affecting the result. And we let it solve because I wanted to try first at least major design and partitioning together rather than just simple change in the cross section. So it looks like I got the job, and then you can create different versions depending on the balance. In this case, is between the product performance, the structure performance, and the manufacturability, which is often translated as a estimated manufacturing cost. And if you have a different balance, you got this lighter weight, very say compliant, and maybe each is just a straight beam, so it's very easy to make, and so on and so on. As opposed to this one, it's got big, really, the things, very heavy, very stiff, but then this one has a big, say, stamping press required, stamping die required. Okay. And we did a little bit better by basically shrinking the unit size of our primitive, so that instead of a beam-like thing, it's more like a tile. Okay, but it's still tile. Principle is the same. You can get a different version depending on the balance between the manufacturing structure performance and the estimated manufacturing cost. Yes, and you can do better even for the smaller tiles, and maybe you can do this, the multi-objective balance between the different objectives, manufacturing, assembly cost, But all these was not too happy because this was really the limitation you can do. Okay, you can do different 2D, maybe finer the mesh and so on, but it's not fast. Why? Because so far at this point we've been doing this as a discrete optimization problem, Why discrete optimization problem? Because naturally, it's a partitioning really is involved. So partitioning is like partitioning, cutting things into 2 pieces, 3 pieces, 4 pieces. So it's a discrete concept. So of course, straightforward thinking that okay, because of that, yes, let's formulate as a discrete optimization problem. And if we probably learn some from your class, that the discrete optimization problem is a nasty. Okay. Because you can do it, but it's not fast. And the clever method exists, but it's not fast enough. Okay. And the flip side of that is it's not scalable. I cannot really solve this, the complex problem that might be even, close to this industrial quality. And I really concluded that was because it's not continuous optimization problem. As long as you're living in the world of discrete optimization or maybe combinatorial optimization, the same thing, those are synonyms, it's slow. Okay. And so I have to really twist my the brain so that, okay, I am dealing with partitioning problem, which is discrete in nature, but I don't like that fact. How can I turn it into continuous optimization problem, so continuous decision problem, which is not too obvious for me for a while. As you see, this is 2013, and today is 2018, so it's not too obvious to me. We've been pondering this one for a while. Yes?
How many iterations?
This one?
Like for these discrete ones?
Yeah, okay, so this result, this was done by, those multi-objective fancy, NSGA2 type of thing, long, even for this type of thing, although you get the multiple outcomes, in one shot, it's a desktop PC back then, took several days to get to the reasonable convergence. So it's really not scalable. Although I put that in the paper and saying that you can get it, right? Without saying how long it took, but it's not really scalable to any type of a problem beyond academic scholarly problems. So I didn't like that. So about 5 years we pondered. I would say precisely about 6 years we pondered. Okay, and then about 2 years ago we came up with a solution of the last one, not continuous. Okay. As long as I can turn this problem into continuous optimization problem, then a whole bunch of sophisticated gradient-based solver, which is, namely, we obtain 1,000-fold speed improvement. That was it. That was really what we are talking about, MTO formulation. So this is, you have, it look like, your potato model in your final element class, right? And the topology optimization is really like changing the shape of potato, okay? Given those various boundary conditions. Okay? And MTO on top of it is to try to figure out, one part versus another within potato. Okay? So that's really the problem. And so if you say that, okay, one blue exists in potato and one red exists in a potato, that is really the discrete concept or the discrete understanding of the problem. So I meaning this, I am being the little part of potato. Okay, little part of potato belongs to blue subdomain. Okay, but not in the red subdomain. Okay, that's the discrete interpretation of the partitioning problem. Okay. But at some point I realized that what's wrong with saying this one? I, being a little part of potato, could belong 80% to this subdomain, this component basically, and 20% to that subdomain, 20% of that component. I, being somewhere in the domain, okay, could fractionally belong to component A and component B. So for the same token, component C and D and E and F all together. Okay. And someone like Glenn said, oh yeah, that's obvious because there's a multi-phase formulation of materials. Indeed, yes. It's actually multi-phase representation of materials. I just rephrased the phase to be component. But it took us for a while to realize that. 3 years to realize that. Then, as soon as you that, oh yeah, this is really the multi-phase problem. A phase being a component. Of course, one engineering difference is that when you talk about material phases, you don't impose additional geometric constraint for the certain phases. But in this case, because it's a component made by certain manufacturing processes, each component is subject to the geometric constraint, which is also additional, I would say, mathematical burden that we have to overcome in order to make this formulation work. But the first problem is solved. Okay. So in terms of a decision variable, I could go from discrete decision variable of figuring out which component I belong to, 100% versus 0% binary decision, to fractional decision. And then you can use continuous solver to figure out the outcome based on certain given objective. And so conventional TO is basically dealing with this one. So it is working with indeed the density field. To credit for the researcher in this field, I guess this is one method in TO that will deal with this density field. Okay, there are several variations exist, but so this is one branch of the method we'll be adopting. So this is conventional. Up above here is the conventional TO. Okay, so you only use this density field. So on top of density field, we basically added this material phase field, which we call as a component membership field. Okay, and this is only one because material can exist or does not exist. But then the component membership field could be should be as many as the maximum number of components you want to consider in the system. And which, I back in my head, which is a little bit of weakness of this formulation in terms of scalability right now, but still, it's better than what we had. So K is the maximum prescribed number of the potential components. Of course, optimization decides later on that you don't need, use all of K. Maybe you decided to only use this part of K, which is okay. But that's really the maximum upper bound you have to specify. That's really the number of fields you have to define. No problem. But if you define this, and then a similar way, really the vector field of the dimension K, then you formulate the problem really elegantly like this. So the conventional TO has only rho as a variable. Now have an n, which specifies a fractional membership. Has to fraction because it has to be lie between 0 and 1, and this unity constraint exists. But then everything else is really similar to the original version. Of course, original version normally considers structural constraint and structural objectives typically. But now, like I argued earlier, that the very reason you want to have a multiple components is that to conform manufacturability of the chosen manufacturing processes. So naturally, additional process-specific constraint has to be imposed to the particular choice of the density as well as this membership variables. So this, as long as existence of the membership field, successfully extend the monolithic TO framework into multiple component framework in continuous optimization. So then what are the say example of constraints imposed by chosen manufacturing processes? And so we worked on several major classes of processes of interest, and realizing that surprisingly the constraints are very similar. Okay. So that if you figure out, say, only handful of a set of geometric property to be constrained, it can be applicable to wide range of manufacturing processes, with of course some tweak, but the principle is astonishingly small. One of that is, of course, the size. Okay, size matters. Typically you have a machine limitation, or maybe the cost of machine is expensive if the parts are big. So being able to impose a size constraint is important for many classes of manufacturing processes. And figuring a size of the first the headache we had in this MTO framework. That's what I say. Okay. in short, how we did it, okay, let me talk about challenge. Challenge of figuring a size is that we are talking about during the optimization of density field, you are talking about really like a ambiguous blob with cloudy blob, okay? So that what defines as a geometry is not really the geometry with the crisp boundary, it's just like a cloud, okay? So you're talking about the cloud floating in the space, and what is the size of that? That is really the problem you're posed. And that's a little bit of a challenge because we wanted to measure the size as a size you would manufacture the parts. Okay? So that may not be really the size of the design domain you start out with. Okay? So you have to really measure the bounding box of the cloud. So how can I measure the bounding box of the cloud? Well, we basically took some approach people do for the data analysis. Basically, we took the weighted principal component analysis to figure out the orientation of the cloud. Okay, and so to figure out the major and the minor axis for the PCA, of course, weighted according to the rho and p values. Okay, and so we view the cloud as a point clouds basically. And then figure out the major minor axis, and then close the bound. Okay, approximately using a continuous relaxation of max mean function, of course, which they call it the heave side, the relaxation. But indeed, what we did was figure out the right orientation to look at by PCA, and measure the maximum and the minimum distance of the point clouds, weighted according to the value of the field value of rho and n. So size is done. Okay. So now let's next length or perimeter length. That's often to do with the measure of the complexity of the geometry from the viewpoint of machining the mold corresponding to the geometry. So any molding process related to like the stamping, casting, you have to really CNC machine the contour of the shape. So it's, in addition to the size itself, which is the bounding box size, which directly translates to this die set size and press size, the contour length is directly related to the machining cost of the die. So the perimeter length is also important for the wide range of manufacturing processes, which is not our invention. Some people, in the topology optimization world, actually come up with this the generalized concept of a perimeter length of the, again, point cloud. Okay, it's always a cloud which gives us a headache. If it's really having the black and white the result like this, which only appears at the end, measuring a perimeter is not a problem. But doing so while the convergence is not done, like everything is looking like a cloud, is a challenge. But we didn't invent it, somebody did it. So it's a generalized concept of a perimeter based on density, and we simply applied it. So this was like a long perimeter versus the short perimeter result. And undercut, of course, that's also the common constraint for many manufacturing process. Not to mention the molding process subject to undercuts. If you have to take out parts from the 2 separating dies or 3 separating dies, you have undercuts. Okay, undercuts in direction of the die mold, the drop is of course the issue. But if you know some about additive manufacturing, undercut is always also the issue for additive manufacturing because basically you cannot deposit or solidify the parts which is too steep in the angle associated with the build direction. Okay. So the undercut is also the issue for additive. And so we tried to figure that out. Well, but then somebody did it. Okay, so we didn't really bother to reinvent the wheel, so that we use this method people created, which is try to measure the undercut as a really the gradient of a density field around a portion of where the things density is very low versus density is very high. So you just look at the gradient, you could approximate undercut values on the certain direction, taking a dot product with a gradient in certain direction. So this was like undercut, lots of undercuts, and this is less undercuts. And the interesting effect of applying this undercut constraint is that it's somewhat a byproduct, but it often actually eliminates the holes for one-piece topology optimization, according to their papers, which kind of makes sense because the hole is often really the cause of undercut. Okay, but if you look at this, really after applying undercut constraint in this direction, okay, why use topology optimization in the first place if that's the result you want to get, right? So that was really the question mark posed by this work. However, if we look at this, the new viewpoint where I am designing multiple pieces, all of a sudden, okay, each of parts can have undercut free, but still as a combination, you can create holes within it to optimize overall structural performance. That actually, it gives you really like a comeback to this type of method. Okay, people ask that why use topology optimization in the first place if it's really the simple blob you're designing. Okay, sure, this is important because parts are manufactured and still you can get the whole geometry like optimized for this one. Okay, if you assume that the multiple components are possible. And somewhat independent of undercuts, there's a method which is only strictly try to eliminate holes. Now, completely enclosed cavities or holes are also the common constraints on many manufacturing processes if you think about it. Okay? Even for additive, you cannot really have a completely closed holes especially for the powder bed process, because where the powder should escape. Okay, not to mention you cannot do that for casting washer. Okay, so this is a common process for many, a common constraint for many processes. And again, we didn't invent it. People figured out for a one-piece designer list. What this does is basically try to simulate the imaginary or the fictitious heat transfer problem, which is originated from this the low density field, which can be a candidate for hole. Okay. And where the material exists, is again a fictitious high insulator, so that the heat generated will be trapped if there's a hole. Okay. And on the other hand, heat will escape if there's exit path from the internal cavity. Okay. And then by constraining the maximum temperature within the hole, you can actually effectively constrain the formation of the hole during the topology optimization, which is a very clever trick. And but then if you apply that, you get a result like this in one piece. And then why use topology optimization in the first place? That's the question. Again, this again will give a good comeback if you consider multiple pieces. Indeed, yes. So things could look like this. This is a size and the cavity constraint applied. So the individual piece is cavity free, but then also the size is confirmed so that it will stay within the prescribed, say in this case, the printer size. Okay, and boundaries created so that they will be joined in the least impact portion in structural map. Okay. And so this kind of tries to illustrate simultaneous emergence of geometry, which is design, as well as partitioning, which is the component. So this is only looking at row. This is pretty much like a one-piece topology optimization we are looking at, and the evolution of the component membership field, as well as its product with row. And this is, really, what looks like individual pieces. Row times M is really what looks like individual pieces of component. Each of them is, of course, subject to process-specific manufacturing constraint. And if you put them together in one figure, sorry, I pressed the wrong button. It is overall what's happening in optimization is that, from the a cloudy gray. Gradually, the shape as well as partitioning is emerging as a result of convergence of the optimization. In the end, you get this a little bit of a boundary, which is a less stiff area corresponding to the joint region. Okay. So this tries to illustrate the nature of coupling between design problem and partitioning problem. why we solve it as a couple problem, integrated problem in the first place is that those are a couple of problems. Meaning that if I change the size, topology changes. Okay? And I try to illustrate that in this example, but that was known fact. Even when we were dealing with the discrete version, we did this brute force enumeration of everything to make sure that that was indeed a couple problem. So that the partitioning and topology design is a couple problem, but then you can quickly demonstrate on a finger snap the size matters in this continuous framework, because it's really fast compared to what we've been struggling in the past. So size changes, then the partitioning as well as overall topology changes together. MTOX. All right, so quickly going through. MTOS is sheet metal stamping and spot weld. So major constraint applied for each component is that overall size of a die set as well as the perimeter length, which is the machining complexity. So that's really what's applied. And so then depending on where you set the allowable bounds in each constraint, you can construct a design with a high cost, moderate cost, or low cost. Of course, has an impact on overall structural performance too, so that your job is to figure out what's the best balance. You can do casting. In this case, in addition to component membership and density field, we have additional variable that specifies this parting line and its orientation. So then the undercut is figured in the direction of parting line. So it's an undercut size constraint as well as undercut constraint, and additional variable for the partitioner. And this is at this point you start to see better resolution figure. That's when we moved the classic, say, mesh-dependent representation to mesh-free representation, which requires a little bit of mathematical tricks. But again, we didn't invent that math. We really tried to use this. Well, people have worked hard to make TO mesh-free, and so we simply use that method to make it really look nice. This is a series of mathematical tricks you do to try to detach the variable representation to underlying mesh, which is often the case required for TO. And so once you do that, then the whole boundary looks nice. It's just a software implementation issue. And so this is supposed to be the MTOC, the Taylor fiber placement composite, so that you place the fibers and you can join using resin. And within each component, there's a certain degree of curvature change is allowed. So that's the additional manufacturing constraint. But because of the process, we don't impose the part to be a single connected piece in this process. So this one is basically like a placing one fiber in one place, another fiber, another place, so that this and this can be practically one part, which is not the case for the other type of processes. But again, we can control this process-specific constraint as long as we know that in a mathematical framework to get the result that I can use. In this case, number of distinct fiber orientation is what we consider as a component, not the physical connectivity between two components. So that these are really one component from the composite manufacturing viewpoint. This is one piece you're cutting and then placing. Okay. And so that's really another tweak of a concept of component applied to this chosen manufacturing process. Then you can do 3D. This was meant to be first attempt of A, which is made like this. And the word of caution is that this is meant to be metal. This was just a demonstration purpose for the Stratasys machine plastic. And for the demonstration only, we made a joint to be Velcro so that you can enjoy assembly and reassembly, which I can distribute. Okay. So you can straight, the result can be straightly sent to the printer, and then you can make things like that. This one is isotropic still, idealized situation. But we made that. There's a little movie my student made, but I guess you have the model, so I don't have to play. Beyond. One thing which is really about to come out from the lab for the publication is the anisotropic version of MTOA. So because additive anisotropic, I have a square. So it's a MTO applied for additive, but the anisotropic material property is also designed, which is really corresponds to the view direction of a component. So in short, in addition to consider the isotropic properties, because we have a knowledge of view direction when you are figuring out the manufacturing constraint and undercuts, we apply that direction to impose this anisotropic material property. Basically, the interlayer property stiffness of the material is far less, at least for now, compared to this other direction. So we apply that. Of course, this is exaggerated, okay, to see the effect of that. But then you can have a 1-part isotropic, 3-part anisotropic as a different configuration. So this was meant to be an interesting demo where the green surfaces are what's fixed, and the little label indicating arrow is supposed to be the loading direction. So all those are on the shear of the unfixed surfaces, and it's made such a way that it will produce some interesting demo. And as you see, if you take this apart, it's actually doing, each part is almost identical because of the symmetry in the loading condition. But then what's done is that very clever cut of what otherwise would look like an eggshell in the middle of this thing. Okay? And I don't even know well how to put them together if once I'm taking apart. But again, I'm circulating so that you can make solve this puzzle by the time it comes back. But this is really result of computation. I didn't do any design, only specifying requirements. And then you will create this complex boundary as well as the cavity in the middle. Cavity in the middle exists as the overall product, but not in individual parts because that was a constraint. But the optimization figure out that's the best strategy to utilize cavity as an assembly, but then I cannot do it within the component because I'm constrained. So that's the very power of MTO framework. Another to be done is joint. Okay, we don't do a whole lot of good in joint, but we are about to be able to do good. One of the criticism of the reviewers I received in earlier publication of MTOA is that the joints are more susceptible for fracture. Okay, can you add the at least stress constraint on the joint region? Sure, and so that's what we are working on. Of course, the challenge is not to impose stress constraint itself, but to figure out where's the joint. Okay, so the region we consider as a joint, especially around the boundary between, is really the headache. Okay, and but we cannot figure out how to do that numerically stable. It's actually really a numerical problem, by the way. Boundary is really the two components collide, so mathematically clear. But numerically figuring out is a little bit of headache. We couldn't solve initially, but now looks like, at least in this figure, it's figuring out where it is. My student said that's not by hand, so it's by computer. So I trust him. It's numerically stable. You basically have the thresholds. Then you can apply stress constraint there in addition to potentially the arbitrary mechanical property corresponding to the particular method of joining, spot welding, seam welding, adhesives that has a different property. And that's something we can do now. As of my email I saw in the morning, looks like it will produce interesting result if you apply different mechanical property to the boundary region. This is something that we are working on as the next the high performance composite. Hope I can have time to play this video because this is very exciting. Oops! Oh, sorry. Same thing happened as in the past. Oh, we cannot see the movie. Can I do that? All right. All right. Looks like that solution worked in a different talk worked. Okay. So this is like doing embroidery, embroidery, right? But this black one is carbon fiber, okay? And it is indeed a fabric. You are putting embroiderment, okay? But with the thread made of carbon fiber, okay? Now, so you have the carbon fiber embroidered fabric, okay? And then you soak it into the resin and then mold it, okay? If you know the fiber composite process, this is amazing degree of curvature you are doing, which nobody actually does it. And this was from a company in Germany, which has, you can find on a website. They boast that you can do this for the fractional weight of itself. So this is very stiff structure, optimized for, of course, the vertical loading. But then high performance comes from this arbitrary choice of fiber direction. In particular, if you look at their video, what they're doing is actually doing, say, multiple path planning of fibers. Because you can lay fibers in arbitrary direction, in this stool, you could actually do this in one path. Maybe another path you are doing this, okay? Another path you are doing this, okay? So that the choice of path is pretty much arbitrary because of the versatility of the process. And that, in combination of the resin molding, provides very superior structural performance. And that's the process we are looking at, our method to apply. Looks like one piece. Where is the component? Well, fiber branching, really, okay? This particular path of fiber is one component. That another path is another component, okay? And that is the principle we are applying our MTO, so that trying to figure out a multi-path fiber layer problem for the high performance composite like this. And which is probably about to come out in a few months. And so this is like continuous fiber printing. That's what the name, at least those people use. And so this is our initial result of the continuous fiber printing problem. Fiber can be oriented, looks like a stool, but you realize that that is not developable, okay? Because it has to start from fabric, at least from that process, and then you remold into the stool shape. So that this represents the class of geometry, like is the CAD people call it a developable shape. So with a certain the threshold of strain, because it's molding, but it has to start from the flat paper, okay, flat fabric, and then molding.
Well, what is the application of this? Who's paying for this? That must cost an enormous amount of money.
This one, we don't work with them, but this one is an independent company in Germany, basically, like a Fraunhofer Institute that they try to develop the C technology potentially.
Is it just R&D, or because unless you send it to the moon or something, nobody can afford to pay for this?
Really is, yes. Space application and some military application is there. So the cost may be high, but the performance is extraordinary. Really, this so different that you can really think of how light this thing and how strong it is. Weight load bearing ratio is amazing.
So you need to make a mold afterwards, right? So you have
Right. That's another headache.
Do this. Okay.
Yes. Okay. Still, this is a molding process, and then of course, if you see their video, manually done for the demo purpose. But so separate mold is created, and then it's sandwiched between molds, and then cured for a few days. And I don't think they bake it, but at least cured for the resin. Anyways, so we kind of could do this, but then it's not developable because we haven't really applied the developability constraint, which is additional manufacturing constraint, or the principle of our talk. Yes, developable constraint, of course, you all know that that exists, so you can actually do a little bit of extension to the applicable for the point cloud rather than the crisp geometry, and so be it. So then we are good to go. So our vision really is that mix them together. We worked on MTO X, but X being not mixed. C, D, A, whatever. Okay. But then really that the ultimate goal should be really the mixture. Multi-material, multi-process, multi-component topology optimization. That's really the goal we are looking at. Oops. So this is just an idea yet. We haven't done it. So basically, if you design things like this, it really should be, using right material at the right process at the right places, so that all of the choices are optimized for, typically for performance as well as cost. Of course, the balance should be taken carefully into account. And that would necessitate maybe in some portion the use of the highly scalable the mass manufacturing processes for some non-critical portion, whereas using something like additive, the expensive material like titanium for the mission critical piece of structures. So that if you could do that, that is really the ultimate goal of this simultaneous design and partitioning approach. We have not done it, but if you kind of extrapolate what you saw, it's actually one step beyond, really. Because one thing missing in terms of mathematical formulation, all the headaches of the practical thing aside, is one more variable that will dictate the choice of material process combination, right? Now, you can apply the same phase field analogy so that rather than I belong to this material process combination and that material process combination, maybe I can belong to 80% to this material process combination versus 20% to this material process combination. Then I'm done. Additional field representing, for each component in this case, material field combination. Okay. Then formulation-wise it's done. So it's a matter of implementing it. Of course, from that on is a headache usually. But math is there. 4D printing. People talk about 4D printing these days. Hope. So we thought, okay, that might be an interesting thing to do. So at least what they do for now in those people is that, okay, I have printed something, okay, and then maybe soak in the water or heat in the microwave or some other thing, and then things start to fold up to some shape. Because it's the time is involved, instead of 3D, it's 4D. Criticism right now, yeah, of course, this is 2.D, but anyways, so that's what people say 4D. And so they, I put out this figure from a web on this MIT self-assembly lab, making this, flappies, and then I don't know, they actually heat it maybe, and then they fold up to make a fancy elephant. Cute. And I was not too excited by this one by itself, but I was excited by the fact that there are two pieces there. So again, always I ask myself that why two pieces? Because maybe they cannot make elephant from one piece. So then that kind of again rings the bell that maybe something that could not be achieved by one piece could be achieved by multiple pieces if you make the multiplication in the right place. So that's kind of what I'm thinking to be a potential direction along the line of what people say 4D, which is really, it's fair to say 2.5 plus 1D, okay, not 3D, because it's a paper really. Takeaway, I'm wrapping up. I hope the time is okay. So we talk about this one, and we talk about that one. And so a sense of MTO framework we developed is really conventional TO. Without it, we haven't done anything. Okay, so that's really important thing. So it's there. Now then, I added the concept of membership field, specifying, allowing fractional membership, okay, of a piece of potato. And manufacturing constraint. Also, that is an important piece that will drive ultimately the partitioning of a single piece structure. So then you can do this. And that's all of my talk.
I am wondering, did you discuss this concept at all with people who are doing optimization in the real world all the time? Because some of the constraints, cost, regulation, weight, these are the things people worry about all the time. You showed some examples where you have two parts assembled together. How do you assemble together? Sheet metal, that's easy. But what if you have extrusion and forging and you assemble together, you cannot weld it. It's so big. I mean, those are practical concerns that people worry about it all the time.
Right. So actually,
You know, for example, that sketch here you showed.
right.
Well, this is also, automotive industry is doing this in a way,
Yeah.
a little differently, but in a practical way.
Right. So a part of the package, of course, which we didn't make too much emphasis, is that figuring out the joining process. So that the dissimilar material joining, dissimilar process joining is the stuffs that has to fit into the overall framework. Just like you figure out the choice of available manufacturing processes, you have to choose the choices among the choice of available joining processes, because if you take the two material combinations, which can be all compatible to certain choice of materials, but maybe there's no method to join, or maybe join property will be different depending on the combination of material as well as combination of the processes used for produce materials. Right? So the equation I didn't really emphasize here is actually this is additional decision variable you have to introduce, and that has to come from the information about and the knowledge of available joining processes. That's the part of the reason. I know I worked with the big project of lightweighting of mixed material and so on, and they are still struggling this portion mostly. Okay, and therefore I keep this one as a kind of still a dream, rather than mathematically it's done. So I can make haste and produces this like a toy story. Okay, but nothing is practical at this point other than being a dream, because people are still struggling to how to figure out property. In the first place, what are the methods to join and what are the corresponding mechanical property of the joint? Without it, I cannot compute reasonable accuracy. So therefore, for that reason, I keep this as a dream story at this point. Maybe a couple of years, some people figure out maybe this combination of materials, this means the method, and the established mechanical property estimation is there. Then I start to incorporate those models into the framework. We have not done it for the very reason we mentioned. Dissimilar material joining, this is heavily under development, and we can really tackle it as a design problem. This is way before the stage we can do any design.
But
Because we are figuring
even
out-
similar materials, you cannot join bulk materials together. If you have sheet materials, that's easier.
Right.
But bulk materials, you have shown some examples where you divide the original design in small parts, and then you say you mathematically on the figures it's easy. If you do additive manufacturing, it's easy, but in reality it's impossible, at least with today's technology.
Yeah. So I agree, and that might require maybe adhesives or the advanced seam welding, or something else with a bolt with flange. Okay. So that is something we haven't really paid, too much emphasis. Therefore, for the very reason, we just leave it as a dream story. Okay.
Let me see
But
if any of the
what
graduate
else should be-
students have any questions. Yes.
Yeah, so you talked about simultaneous design and partitioning. So at the beginning of the design, we have just a bounding box, right? So how do we decide about the partition boundary or the number of partitions that we can have? What are the deciding factors for determining the partition boundary and the number of partitions?
Maximum allowable number of partitions is k, which is as given constant you have to give, and somewhere between 0, I would say somewhere between 1 and k, optimizer will decide what's the best number of partition, and that's the outcome of optimization, which is the result of optimizing given objectives, which is typically structural objectives like the compliance, subject to manufacturing constraint, and as well as weight constraint. So number of partition is decided somewhere between 1 and k. K is given number as a result of optimization, of minimizing objective function subject to certain constraints.
So that K is something do you give while designing, or is it like a heuristic algorithm that the algorithm itself
K is an
uses?
input to the problem.
It is the input.
Yes, user's choice. Any other questions from our students? So, yeah, go ahead.
That's a quick question. So the size constraints, you're basically using kind of the heavy size filtering, the size constraint.
Yeah, after
and
figure
the
out the orientation, yes.
manufacturing.
Yes,
So
yes, yes.
okay,
Yeah,
so it's
so-
kind of a filtering technique, like the heavy side filtering. That's what you mentioned.
Yes, I mean, after you figure out the orientation, then you have to take, the centroid,
Yeah,
and then
yeah.
measure the maximum along the major axis, minimum, and so on, right? And the optimizer does not like min and max, so therefore you take the relaxation.
Yeah.
So, where is it? Oh yeah, here. Oh, okay. Well, yes, yes.
Yes,
So,
thank you.
but first you have to figure out the orientation, which is done by PC.
Well, there's another seminar here right after, so we
Okay.
have to vacate. Thank you very much.
All right, thank you.